Hi everyone, welcome to Easy BTech. Today I will teach constructional details of practical DC machine. So this may ask for 10 marks in JNTH examination. So what are the major parts are there in DC machine? The first part is yoke. The first part is yoke. And second part is pole core and pole shoe. And third part is field winding. And fourth is a very important armature winding, and fifth is commutator, and sixth brushes, and seventh shaft. So this is a cross sectional view of a DC machine. The outermost part is called the yoke. The outermost part of a DC machine is called the yoke. And if you observe this one, and this part is called the field poles, and the brushes are there. So this is a small part. The small parts is called the brushes. So this part is called the shaft, and here if you observe the wave, if you observe the part, so this part is commutator. This type of part is called the commutator. What is the purpose of yoke and what is the purpose of pole core and pole shoe? We'll discuss one by one. Yoke is made up of, it is made up of cast steel for large machines. Cast steel for large machines. Cast iron for small machines. Cast iron for small machines. And it should be in a hollow cylindrical shape. Hollow cylindrical shape. So if you observe this is the outer part of a DC machine, and this part is called the yoke, and this is fitted to the panel with the help of a bolts. And yoke is made up of cast steel for large machines and cast iron for small machines, and it should be in hollow cylindrical shape. What is its function now? The first function is it gives mechanical support for field poles. Mechanical support for field poles. So in the last session, in the previous session, we discussed about North Pole and South Pole is like this. Here we are having a field winding. This field winding is excited with DC. It will produce as a magnetic field. So these field poles are attached to the yoke. So this is the outer part. If you observe, this is the outer part. This outer part is called the yoke. The field poles are attached to the yoke with the help of a bolts or welded to the yoke, and it gives a mechanical support for the field poles, and also it acts as protecting cover. It acts as protecting cover for the entire machine from dust, okay, rain, and it will be avoids. There is no contact to the external things, that is just like air, is a dust. So it acts as a protecting cover for entire machines. And the first part is it gives the mechanical support for field poles. And third is the most important, it provides low reluctance path, low reluctance path for field poles. Flux is equal to mmf by reluctance. If the reluctance value is low, then the flux distribution is more. Externally, the flux lines are flowing from north pole to south pole. Internally, the flux lines are flowing from south pole to north pole. In order to complete its path, it is south pole to north pole. And it should consist of a low reluctance path. Then only the maximum number of flux lines are passed through this yoke. And coming to the second part is pole core. Pole core. And this part is called the pole core. And the edges, if you observe this part, is pole shoe. On the pole core, what is its function? On the pole core, we wound the winding, the field winding is wounded on pole core. And when it is excited with the DC supply, when it is excited with the DC supply, then it produces magnetic field. Then it is produces a magnetic field. So field winding is wounded on pole core. When it is excited with the DC supply, then it produces a magnetic field. So the field winding is wounded like this. The current passes through here, and then it acts as a north pole. It will produce a flux. And this pole core is fitted to the yoke with the help of a bolt. So pole shoe, why the shape of pole shoe is like this means, if the shape of the pole shoe is like this, if you wound the winding is on the pole core, so there is no mechanical support. The windings are easily comes out from this pole core. For that, we are providing a mechanical support with the help of pole shoe. The shape of the pole shoe is like this. So what is the function of pole shoe means? Pole shoe, it gives mechanical support for field winding. Generally, the pole core is not laminated, but pole shoe is laminated because to reduce eddy current losses. We will discuss what is meant by eddy current losses once armature core is, so eddy current losses. And this is about the pole core and pole shoe. And one more major part is there. In this armature, we have an armature core and armature winding. So the third part is called the armature core. So this one is the armature core. Generally, the armature core is made up of silicon steel. It is made up of silicon steel. Why we are using silicon steel means, for a silicon steel, the hysteresis coefficient is less. That is 1.6 for silicon steel. The hysteresis loss is equal to neta Bmax per x FV, where neta is called the Steinmetz coefficient. Steinmetz much coefficient, and F is the frequency of the supply. F is the frequency of the supply, where V is the volume of the core. Volume of the core. So what is meant by hysteresis loss? Hysteresis loss. So the power required to change the orientation of the molecule is called hysteresis loss. If you take a core material during positive half cycle, the orientation of the molecule is like this. The orientation of the molecule is like this. During negative half cycle, the orientation of the molecule will be opposite direction. We know that the frequency is 50 hertz. Okay. So anyway, the EMF which is induced in a DC generator or AC generator, whatever it may be, it is a sinusoidal waveform, right? That means alternating one. Okay, we will change the waveform for DC machines. Uh, so we prefer the flat topped waveform, but it is an alternative. The time period for this one is 20 milliseconds, and half of the time period is 10 milliseconds, and this one is 10 milliseconds. Within 10 milliseconds, what will happen? The molecules will be changes to north pole, and again it will changes its direction in a very faster rate. So during this time, some power is wasted. That loss is called the hysteresis loss. Suppose I will give one example. If you ride a bike on the road, if a straight road is there, you will go with very high speed, 60 kilometers per hour or 70 kilometers per hour. But if a curved roads are there, you will not go with same speed. You will reduce your speed definitely. So same like that, the power required to change the orientation of the molecules is called the hysteresis loss, or the area under the BH curve. The area under the BH curve, where B is called the magnetic flux density and H is called the magnetic field intensity. B is the magnetic flux density, H is the magnetic field intensity. So the BH curve, the area of BH curve is less for silicon steel. Less for silicon steel. That's why we prefer silicon steel. If you use silicon steel means the hysteresis loss can be reduced. So we are taking a singleton alternator, or this is a one turn, right? Yes, or one turn means two conductors. If I am taking the coils, so many number of coils are like this, where I have to kept. So I will take the coils where I have to kept. We require one device, sir, no, that we require one part, and that part is called the armature. That part is called the armature core. The outer periphery of the armature core is slotted in order to accommodate the winding. In order to accommodate the winding. So here we are on the winding like this. Okay, and this air holes are provided. See, if you observe, these holes are provided for cooling purpose. When it is rotating, with 1500 rpm or 1400 rpm, some heat will be produced. So in order to cool down this winding, and the holes or air holes will be provided. And here you can observe, we want to insert this shaft in this small hole, and here shaft key is provided. Once the shaft is inserted and key is pressed, it will be locked. Then the armature is rotating. What will happen if it is not at all laminated? Some EMF is induced. Why? Because core has conductivity. Core has conductivity. Core has conductivity. Due to this conductivity, the EMF which is induced in a machine is alternating. So E is equal to BLV sin theta, right? E is equal to Emax sin theta. If the core has conductivity, what will happen? The core has conductivity, and this armature core is driven with the help of a prime mover, either it is a clockwise or anti-clockwise direction. It will be rotating, then it will cut the flux. An EMF is induced in a winding, that is useful. In addition to that, there is some EMF is induced in core. EMF is induced in a core. Since it is a closed one, the current is flowing through the core. That current is called the a D current. The EMF which is induced in a core is called the a DEMF. Since it is a closed circuit, the current will flows, then eddy currents are formed. And since it has a resistance I square R losses, eddy current losses are produced. Eddy current losses are produced. The eddy current losses are produced. The eddy current losses is equal to K into B max square F square T square, where B max is the maximum flux density. Maximum flux density in Weber per meter square. F is the frequency of generated wave. Frequency of generated wave. And T is the thickness of laminations. Thickness of laminations. If we provide the thickness of laminations as T is decreases, then eddy current losses also decreases. Once again, the EMF which is induced in a winding is a useful one. The EMF which is induced in a armature core is a useless thing. The EMF which is induced in a armature core, due to the alternating nature of the induced EMF, which is induced in a core because of cutting action, and that current is called the eddy current. It consists of a armature core, consists of a resistance. Eddy current losses are also produced. By providing the laminations, we are reducing the eddy current losses. And that is about the armature core. And next one is armature winding. Armature winding. Generally, the armature winding, it is made up of copper. Why? Because copper has a low resistance. If it consists of low resistance, means I square losses is also less. Then the heat produced is also less, and life of the copper winding is more. Life of the copper winding is more. So coming to the armature winding, there are two types of windings. One is a lap winding, and second one is wave winding. Lap winding and wave winding. For the lap winding, number of parallel paths is equal to number of poles. For wave winding, the number of parallel paths is equal to 2. So we'll discuss in detail armature winding in the next video. And after that armature winding, we have a commutator. The next part is a commutator. So commutator acts as a mechanical rotating rectifier. Mechanical rotating rectifier. The EMF which is induced in an armature conductor is an alternating. Is an alternating. This negative of cycle is converted into positive of cycle with the help of this commutator. So once you will check it, what is a commutator now. This part is called the commutator. So this part is a commutator. So generally we prefer the flat tapped waveform. Flat tapped waveform. Rather than sinusoidal waveform, the generated wave in an armature conductor we prefer the flat tapped waveform. If it is converts the negative of cycle into positive of cycle, then it looks like a pure DC. If the number of coils are connected like this, the number of coils are connected like this, and the negative of cycle is converted into positive of cycle, so then I will get the pure DC. So pure DC with the help of a commutator. So let us check it. The commutator operation. So I am taking a two pole machine, the north pole, and this pole is south pole. I am taking a simple loop generator. The conductor AB is like this. The conductor CD is connected like this, and the conductor AB is fixed to the commutator segment X, and the conductor CD is fixed to the commutator segment Y. Between the commutator we are providing insulation. So this part is called the commutator. This part is called the commutator. Commutator. This is a brush B1, and the brush B1, and this is brush B2. Brush B1 is always in contact with the conductor which is existing under the north pole, and here I am connecting one bulb electrical load. Let us say the load terminals are M and N. So as we discussed earlier, the direction of the induced EMF is known by Fleming's right hand rule. If these conductors are rotating in a clockwise direction with the help of a prime mover, P dot M means prime mover. So what is the induced EMF direction? So here the tangential force will be upward direction, here it will be downward direction, because it is rotating in a clockwise direction. It is rotating in a clockwise direction. Thumb indicates the motion of the conductor, forefinger represents the direction of the magnetic field, and middle finger represents the direction of the induced EMF. The direction of the induced EMF, right? so it will be into, and it will be dot. So here the tangential force is downwards. The flux lines are coming from north pole to south pole in this direction, and this middle finger represents the direction of the induced EMF is outward. So the current direction is from A to B, and after the C2D coming here, and the current is not flowing to X. Why? Because in between, so mica insulation is provided, and there is no other option. The current leads through brush B2, and the current flows through N and M, and again it is brush B1. So after half rotation, what will happen? The conductor CD, the conductor CD comes under the north pole. The conductor CD comes under the north pole, and conductor AB comes under the south pole. So the brushes positions are fixed. So brush B1 is always in contact with the conductor which is existing, the conductors which is existing under the north pole, and brush B2 is always in contact with the conductors which is existing under south pole. So again it is rotating in a S clockwise direction. This is the tangential force acting on the conductor CD, and the tangential force is acting on the conductor in the downward direction. So again, if you apply the Fleming's right hand rule, thumb indicates the motion of the conductor is upward direction, forefinger represents the direction of the magnetic field, and middle finger represents the direction of the induced EMF. So here it is cross, and here it is dot. Let us see. So the current direction is from D to C and B to A. So previously it is A to B, C D, A, B, C, D. Now it is D, C, B, A. Now it is reversed. And the brush B2, the current leaves brush B2 to N to M, after that brush B1. See, observe the load terminals. Observe the load terminals. The current direction will be from N to M. In the case 1 is also N to M, and a case 2 is also N to M. That means negative of cycle is converted into positive of cycle. Negative of cycle is converted into positive of cycle. So commutator acts as a mechanical rotating rectifier. So commutators are made with hard drawn copper. So the commutators are made with hard drawn copper, and in this number of commutator segments is equal to number of armature coils. Number of armature coils. And the next part is about brushes. See guys, so brushes are made up of carbon, and to collect the current from the armature in a generator, we are using a brushes. To give the current to the armature winding for a motor. So generally the brushes are made up of carbon. So what are the advantages of the carbon? Means carbon has high resistance. Then we can improve the commutation process. tau is equal to L by R. If R is more, then the time constant will be decreases. And the second part property, it consists of self, it has a self lubricating property. Lubricating property, that means polishing in nature. It is not easily damages. Polishing in nature. And one more thing, it consists of high thermal stability. High thermal stability. That means it can withstand it can withstand for higher temperatures also. Higher temperatures also. And generally, if the brushes are made up of electrographite electrographite and copper graphite, this electrographite is used for large and normal rating of the machine. Normal rating of the machine. And copper graphite is used for the large currents, large currents and low voltage applications, low voltage machines. And number of brushes is equal to number of poles in lap winding. So number of brushes is equal to 2 in wave winding. Okay, and this is about the brushes. And after that, the shaft is made up of mild steel. And this is about the construction of a DC machine. So once again, yoke is made up of cast iron for small machines and cast steel for large machines, and it is in hollow cylindrical shape. It gives the mechanical support for the field poles, and it acts as a protecting cover for entire machine. It provides a low reluctance path for the magnetic field. And the field winding is excited with DC. It is made up of copper. It will produce a flux. Armature winding is also made up of copper. And before that, armature core is there. Armature core is made up of silicon steel to reduce hysteresis losses. And the laminations are provided in order to reduce the eddy current losses. And the commutator is made up of hard drawn copper, and it acts as a mechanical rotating rectifier in DC generator. In DC motor, it acts as a mechanical rotating inverter. The brushes are made up of carbon, and electrographite is used for large and normal rating of machines, and copper graphite is used for the large current and low voltage applications. And the shaft is made up of mild steels. So this is about the constructional details of practical DC machines. So definitely